Hello, Math 30-1 students. In today's lesson, we're going to look at solving more complicated exponential and logarithmic equations. And as you can immediately notice, I do not have access to a digital copy of the Smart Notebook file for this particular lesson. So what I will do instead is I'm just going to pick specific example problems, and I will just go through the method and procedure that needs to be carried out and also the work that needs to be shown to solve those particular equations. And I'm not going to do every single one of them. So with that being said, let's actually go immediately to the first example on page 260. And for that first example, there's actually a couple of equations we're going to solve. So for part A, we have two of them. We have equation I, which is we have log of x squared is equal to log of 16. And then we also have a second one, which is 2 log of x is equal to log of 16. Okay, let's start off with the first one here. Now, this one's not too bad to solve. What I can see is each side of the equation is already written as a single logarithm. The two logarithms have the exact same base. I mean, the base is hidden. It would just be a base of 10. So if you have a single logarithm on each side, each logarithm has the same base. You can just set the two arguments equal to each other. So you would just take the two arguments, so x squared, and set that equal to 16. And then you need to solve for x. And if you do that, take the square root of this side, take the square root of that side, and then I would have x would be equal to plus or minus 4. Now, we're going to introduce another step here. We also need to, once we find out a solution, we need to verify that the solution is going to be correct. So the way to verify it is once you figure out your solution, you then plug it back into the original equation and you just test to see if both the left and the right-hand side of the equations are equal. If they are, there's no problem. If they aren't, then you have what's referred to as an extraneous solution. And when we get to that step where we do have an extraneous solution, I'll kind of identify what the thing is that you're trying to check for to see if the solution works out or not. So let's show some work for verifying, and I'll write this down by saying verify x is equal to. Now you technically have two solutions here because you both have plus 4 and negative 4, but I can actually evaluate both solutions at the same time. So we'll say verify x is plus or minus 4. And the way to do that, again, is you're just going to take it and plug it back into the original equation. So what this would look like is you'd have log. And then in the place of x, I'm going to replace it with plus or minus 4, all squared, would be equal to log of 16. And then whether it's plus 4 squared or negative 4 squared, you then have log of 16 on the left side. You'd have log of 16 on the right side. And because both those sides of the equation are the same, it's verified, which means this solution up here is correct. So I'll actually box it now because I have verified the solution. Okay, now this one, I have 2 log of x is equal to log of 16. And I'm going to try to, again, just solve it algebraically. Now, the main difference between this one and this one over here is that you have a coefficient in front of one of the logarithms. Now, if I want to be able to set the two arguments equal to each other, I cannot have a coefficient there. So in front of this log. So what I need to do is use the power rule to bring this coefficient up to the exponent of this argument. So if you do that, you then have log of x squared would be equal to log of 16. Now, if you look at the two equations, this equation and this equation are the exact same thing. So in terms of solving what the equation would be, well, do the same thing again. Just set the two arguments equal to each other. X squared is equal to 16. Take the square root of both sides of the equation. Square root of this side, square root of that side. And you'd have x is equal to plus or minus 4. Now, again, when you verify, what you have to do is you need to plug the value, the solution into the original equation. So the values for x equals plus or minus 4, I'm going to plug back into this original equation, not the equation where I use the power rule to move the coefficient to the exponent. So now things are going to get a bit messed up here. So we're going to verify the two solutions separately. So we're going to say verify. Let's do the positive solution first. So we'll say verify x is equal to 4. And let's plug it into the equation up here. So we'd have 2 log of 4 would be equal to log of 16. And again, I want to show both the left and the right-hand side are the same. So what I'll do is I'll take this coefficient, use the power rule, and put it onto the exponent of the argument. And then I'd have log of 4 squared would be equal to log of 16. 4 squared is 16, so you'd have log 16 is equal to log 16. So no problem, that solution verifies. Now I'm also going to verify negative 4. So let's say verify x is equal to negative 4. And I'm going to take that, I'm going to plug it into the original equation. Again, anytime you do a verification, it must be in the original equation unaltered. Now, if I do that, you then have 2 log of negative 4 would be equal to log of 16. Now, the problem right here is if you plug into your calculator, you can go ahead and try this, just like plug it into your calculator. If you plug in 2, and then in brackets log of negative 4, you're going to get an error. I think it's a domain error. So the problem right here is that you cannot evaluate the left-hand side of the equation because the argument of the logarithm has to be positive. And if it's not positive, then that solution doesn't properly verify. So I'll just clarify this here. So we'll say cannot calculate negative argument. So that makes the solution x equals negative 4 an extraneous solution. So the only true solution to this equation would be x is equal to positive 4. Okay, I can write down here x equals negative 4 is an extraneous solution. So there's really two things you're looking for when you verify. So just the kind of checks right here when you verify a particular logarithmic equation. So let's say you have like log A and then B. For it to verify, you need two things to be positive. So we'll say to verify, both the base and the argument must be positive. If they aren't, you can't verify, and that'll make the solution you're subbing back in an extraneous solution. Okay, now let's just go down to a graph here and just quickly look at what's going on. So part B just wants us to graph it. Now I don't have access to the TI SmartView emulator, so I'll just show you like what I would actually do with these. Okay, so for the first one, what I would do for part I is into my calculator in y1, I would plot in the equation log of x squared. In y2, I'd plug in the equation log of 16. And then just hit zoom standard. And then you want to use the intersect feature. So if I do a quick sketch of what the graph would look like. So here's my y-axis. Here's the x-axis. Okay, we're going to have a horizontal line at some value. A little horizontal line like this. I think that's y2. And then y1 is going to look something like this. It's going to kind of come up and go towards the left. And it's going to be a mirror image as well. It's going to come up and it's going to go towards the right. And then you're going to have two solutions. So you're going to have a solution right here. Okay, call that solution 1. And that's going to be x is equal to -4. Then you're going to have a solution right here, which is x is equal to +4. Now, if you look at the original equation, typically logarithmic functions only exist past to the right of the y-axis, because like they can't be equal to 0, they can't be negative. But so here, you definitely do have a vertical asymptote at the y-axis. X cannot be equal to 0. But because we're squaring x, you are allowed to have negative numbers. So that's why x equals -4 is a solution that's allowed. Now, if we compare it to this other equation, so for part 2, so what I would do is I would plug in to y1, I would have 2 log x, y2, we're going to plug in log 16. Just do a quick sketch of the y-axis, quick sketch of the x-axis. And then what this would look like is, once again, you'd have a horizontal line representing y2. I guess I should have put arrows at the end of it. Okay, arrows there and there. Now, this graph is only going to have the right-hand side. And if you use the intersect feature, you're going to get that this solution, we'll call it solution 1, is x is equal to 4. Now, the reason that you only have this positive solution is, if we go back up to the original equation, well, in the original equation, the 2 is not attached to the x squared. Okay, it's a coefficient. So if you were to plug in log of -4 here, well, you can't have log of a negative argument. So the only values of x that are allowed in this particular equation are positive values, which is why we're only allowed to use the positive solution there. So part C says explain why the solutions are not the same, even though 2 log x can be written as log x squared. Well, again, the whole idea is, for this equation, you can't plug in negative values for x, because you're actually evaluating a negative argument. Right here, it doesn't matter because you're just going to square them, so it doesn't make any difference. Okay. All right, let's go to another example problem. So this is now going to be on page 261. Okay, so this is example number 2 now. Okay, the equation I have is log. This is for part A. Okay, so we got log with a base of 4 argument x plus 1, and then minus log base 4, 2x minus 3, and that's going to be equal to log with a base of 4 and an argument of 8. Now, this one's a bit tougher than the previous one because the previous one just immediately started off having a single logarithm on each side. So what I want to do for this one is on the left-hand side of the equation, okay, we want to have a single logarithm. Once I have a single logarithm, then I can set the arguments equal to each other. So I want to write down these two expressions with a single logarithm, which I can do because they have a common base. Okay, so we'll write it down with log with a base of 4. Now, because you're subtracting the two logarithms, that's going to make use of the quotient rule. So the quotient rule is we're going to divide the arguments. So that's going to be x plus 1 over 2x minus 3. And then that's going to be equal to log 4, and then with an argument of 8. Well, now what I have is you have a single log on each side. There's no coefficients in front of them, and they have the same base. So now I can just set the two arguments equal to each other. So we'd have x plus 1 over 2x minus 3 is going to be equal to 8. So again, we're just taking the two arguments and we're just setting the arguments equal to each other because everything else is constant. Now, what I'll do is we're going to move this 2x minus 3 up to the top. Although I just want to make a quick note right here that there is a non-permissible value, which is x cannot, like the denominator cannot be equal to 0, which means x cannot be equal to 3 over 2. Okay, that might be something we have to deal with in a bit, but I don't think we actually have to do it in this question. So we'll put this in brackets. We're going to cross multiply, and we'll bring that up to the top. So this would then look like x plus 1 is equal to 8, and then 2x minus 3. And this is going to be a linear equation we have to solve. So to do that, we'll just multiply the 8 and using the distributive property. So to have x plus 1 is equal to 16x minus 24. And then what I want to do is I want to get the x's on one side, and I want to get the constant terms on the other side. So the way I'll do this is we're going to subtract x from both sides, subtract x, add 25 to both sides, add 25, or 24, I should say, not 25. Getting one step ahead of myself there. Okay, add 24, add 24, and then what I would have is 25 would be equal to 15x. Get x by itself, so divide both sides of the equation by 15, divide by 15. Okay, the 15 cancels off here. 25 over 15 is a fraction that reduces to 5 over 3. So if you divide the top by 5, it's 5. Divide the bottom by 5, it's 3. And then my potential solution is going to be x is equal to 5 over 3. Okay, but I need to make sure that this is not going to lead to an extraneous solution. So an extraneous solution, again, is the issue if you're going to get a negative argument or a negative base. So I'm going to take this solution, x equals 5 over 3, and I'm going to plug it back into the original equation and see if I can make both the left and the right-hand sides the same. So if you do this, this would then be log of 4, and then we have 5 over 3 plus 1. So again, I'm just subbing in for the place of x, 5 over 3. And then minus log with a base of 4. And then this would be 2 times 5 over 3 minus 1. Okay, this would be equal to log 4 of 8. And let's try to clean this up a little bit. So I want to get a common denominator for this argument. So the way to do that is I would write this as 5 over 3 plus 3 over 3. Okay, 5 over 3 plus 3 over 3 would be 8 over 3. And then here, this would be equal to 2 times 5 over 3 would be 10 over 3. And you want to subtract 1, so let's write 1 as a common denominator of 3. So that'd be 10 over 3 minus 3 over 3, which is... oh, sorry, that's not a 1 there, that's a 3. My bad, let's fix that. Yeah, that's a... let's fix it in green. Yeah, it's minus 3. Okay, so sorry. If that's minus 3, then we want to write 3 with a denominator of 3. So that would be 9 over 3. Okay, so that would be 1/3. Okay, so then this would be log 4 with an argument of 8/3 minus log 4 with an argument of 1/3. And we just want to see if that's equal to log 4/8. Okay, so again, these two right here, we can combine with the quotient rule. So we can write the single logarithm. So it'd be log with a base of 4. And then we write down, you have 8 over 3 on the top divided by 1 over 3 on the bottom. And that would be equal to log with a base of 4 and then an argument of 8. Okay, so what happens here is the 3 on the bottom and the 3 on the bottom cancel off. And then that would just tell you that log with a base of 4, argument 8 is equal to log 4/8. Both the left and the right-hand sides are the same. So now we can go back and we can just box this solution because it does properly verify. Okay, let's go up to part B. So part B is we have log with a base of 6 and an argument of x plus 4 is equal to 1 minus log with a base of 6 and then an argument of x plus 3. Now, this is immediately more difficult because two of these terms are written in terms of logarithms, but one of them is not. It's just a constant 1 by itself. So my idea with solving this one is I'm going to try to get the log terms on the same side and see if we can simplify, and we'll kind of go from there. So I will take this one, and we're going to add log 6, x plus 3 to both sides, log 6, x plus 3 to both sides. And then what I'll have is I would have log 6, x plus 4, plus, we can't combine these logarithms yet. We'll deal with that in a moment, okay? Plus log 6, x plus 3 is equal to 1. Okay, now let's combine them. And we do that using the product rule because we're adding two logarithms with the exact same base. There's no coefficients in front of them. So it would just be log 6. And then the product rule would just be multiply the arguments together. And that's going to be equal to 1. Now, the issue here compared to the previous one is in the previous ones is we had a log on each side and we were allowed to just set the arguments equal to each other. Well, this one here isn't written in terms of a logarithm. So there's a bit of a different way that I want to deal with this. So what we're going to do is we're going to take this. This is an equation in logarithmic form, and we're going to turn it into exponential form. So if I take this equation and write it in exponential form, it would be you take this base and raise it to the power of this number on this side, which is 1. So write down 6 to the power of 1 would be equal to x plus 4. and then x plus 3. Okay, so again, the whole idea right here is this was just me converting to exponential form. Okay, we don't need to write down 6 to the power of 1. This right-hand side, we can FOIL that out. So that would be x squared plus 3x plus 4x plus 12, which would just be, you can combine these two together to get 7x. Now, that's a quadratic. To solve a quadratic, I want to get all the terms onto the same side. So we're going to subtract 6, and then I would have 0 would be equal to x squared plus 7x, and then 12 minus 6 is going to be plus 6. Now, this is a quadratic that can factor using inspections. You just have to identify two numbers that add to give you the middle number and multiply to give you the constant. So that would be 6 and 1. So you'd have 0 is equal to x plus 1, and then x plus 6. And this is going to lead you to two potential solutions. So x will be equal to -1 and -6. Okay, now what I need to do is we're going to plug this back into the original equation and see if it verifies. Okay, and again, the main thing we're looking for is we want to make sure the arguments and the bases are positive. And if they are, then there's probably not going to be a problem, but let's see what happens. So let's start off with x equals -1. By the way, when you're verifying, please write this out. Like, communicate to me you're verifying. So say write down this as like a statement. Verify x equals -1. Okay, we're going to take -1. We're going to plug it back into the original equation in these two spots. And if you do that, you would then have log 6. And then we would have -1 plus 4 would be equal to 1 minus log of -1 and then plus 3. So this would be log 6, 3 is equal to 1 minus log of 2. Okay, both those arguments are good. So there's not really an issue with, there's not really an issue with, sorry, I just got distracted by something on my computer here. There's not really an issue with the argument being negative. Okay, so now it's just a matter of showing that both sides of the equation are the same. Now you can just plug this into your calculator. Like you can use the change of base identity. So what I would do is you can just write down this as log 3 divided by log 6. And that would be equal to 1 minus. This log has a base of 6 as well. Okay, so this would be 1 minus log 2 over log 6. And then what you should get on each side of the equation is it's roughly equal to 0.61. Okay, so 0.61, 0.61, and then check mark. Okay, that verifies. Now let's try the other solution. So we'll try to verify that x is equal to, the other potential solution was -6. So just as this equation right here, we'll just replace -1 with -6. So we'd have log with a base of 6. We'll plug in -6 plus 4 would be equal to 1 minus log, and then -6 plus 4. Yep, that looks like a 9. So let's fix that. Okay, so then I would have log with a base of 6 and an argument of -2. That's immediately a problem. 1 minus log. Oh, that's a 3 there. Sorry about that. -6 plus 3. Minus a log of -3. So this doesn't verify because you cannot evaluate logarithms that have a negative argument. So we'll just say cannot evaluate. Which means that x equals -6 is an extraneous solution. So we'll cross off this one, and then the only solution would be x is equal to -1. Okay, let's jump down to this next one here. So we have example 3. Okay, so we have 2, and then log with a base of 3, x minus log with base of 3, x plus 3 minus 3 is equal to 0. Okay, now, if I look at this starting equation, I can see I have a couple of logs with common bases. That's good. Okay, what's not good is there's a coefficient in front of this one. So we're gonna have to deal with that in a moment. You also have a constant term right here that doesn't have a log attached to it. So my general idea is I'm going to eventually try to combine these two together. So we'll have these two on the same side. But that constant term, I just want to get to the other side. So we'll move that to the opposite side. Okay, now, if you do that, now again, once I move the 3 to the other side, I want to combine these two logs. I can't do that if that coefficient 2 is in front. So I'll use the power rule to move that 2 to the exponent of the argument. So then it would look like log with a base of 3 and an argument of x squared minus log with a base of 3, argument x plus 3, and that would be equal to 3. Well, now you can combine these two using the quotient rule. So that would be log, and then you would have 3. So the difference, quotient rule, is we're going to divide. So we'll have x squared over x plus 3 is equal to 3. And because on one side you have a logarithm and the other side you don't, this is just an equation in logarithmic form. And what I want to do is just convert it into exponential form to solve the equation. So if you take this equation and convert it into exponential form, it would be this base to the power of the number on the other side. So that would be 3 cubed would be equal to x squared over x plus 3. And I'll just make a quick note right here. There is a non-permissible value, which is x cannot be equal to -3 for that denominator. Okay, 3 cubed is 27. So we have 27 is equal to x squared over x plus 3. And then what I'm going to do is we're going to take this and we're going to move it up here, cross multiply. And then this would be 27. And then I have x plus 3 would be equal to x squared. Okay, let's multiply this out. So it would be 27x plus 81 is equal to x squared. And this is a quadratic, so I want to get everything onto the same side. So we will subtract 27x, subtract 81, minus 27x, minus 81. And then this is going to be x squared minus 27x minus 81 is going to be equal to 0. Now, unfortunately, this is a quadratic that is not going to nicely simplify. So now there are solutions. It's just it's not going to factor well. So what we're going to do is we're going to use the quadratic formula to figure out what the solutions are. So the quadratic formula requires me to have the quadratic written in this form: ax squared plus bx plus c is equal to 0. So your value of a is the coefficient on the x squared, which is 1. B is the coefficient on the x, which is negative 27. And then c is the coefficient, the constant term, which is just negative 81. Okay, so plugging into the quadratic formula, we would have x would be equal to negative b. This is on your diploma formula sheet, by the way. Negative b plus or minus b squared minus 4ac, all divided by 2a. Plug those values into the equation. So negative b would be negative 27, and then plus or minus the square root of b, which is negative 27, all squared, minus 4 times 1 times negative 81. Okay, divide this by 2 times a, which is 2 times 1. And then this would be 27 plus or minus the square root of 1053 divided by 2. Now, the question does say we can write this to 2 decimal places, so there's no need to try to break that radical down into a more simplified one. And if we do that, so the first solution would just be 27 plus the root divided by 2. So that would give you an answer that would be 29.72. Okay, the second solution would be 27 minus the root over 2. So that would be negative 2.72. And then you would need to verify. I'm not going to show the work for verification here, but if you do take x equals 29.72, you plug it into like the original equation, you can immediately see that the negative 2.72 solution doesn't verify because it would be log with a negative argument. So that one doesn't work. Otherwise, like the 29.72 solution does work. So just to save some time here, I'm not going to show what the verification looks like, but this one is extraneous. This one is the correct solution. If you do want to check out my work to see what the verification looks like, just look at my completed set of notes on D2L. So even though I'm not showing the verification here, just be aware that like I will fully expect you to verify solutions if I present a written response problem to you on some form of assessment. Okay, let's go to example 4. So again, we're just making these like progressively a bit more complicated. Okay, so this one we have is we have log with a base of 2, and then I have log with a base of x, and then 3x plus 4. And then this is equal to 1. Now, immediately, this is a nightmare to look at because you have a logarithm within a logarithm. Now, the idea of how I want to solve this is let's make a little substitution to make this a bit easier to look at. So we'll just say here, we'll just say set equal to, let's pick a variable. Let's just pick z, okay? So that entire thing in the square brackets right there, we're just going to make that equal to z. So then I would have log with a base of 2 and an argument of z would be equal to 1. Okay, now that's similar to one of the previous forms where you have a log on one side, a number on the other. So we're going to turn this into exponential form. So this would be 2 to the power of 1 would be equal to z. Now what I'm going to do is I'm going to sub this expression back in, okay? So in the place of z, everything in the square brackets we're going to put back in there. So this would be 2. 2 to the power of 1 is 2, would be equal to, and then I would have log with a base of x, and then 3x plus 4. And now I have just a single logarithm. And I'll use a similar idea here. If you have a number on one side, a log on the other, we can then just turn it into exponential form. So here, this would look like you take this base, you square it, and that would be equal to the argument that you see. So it would be x squared would be equal to 3x plus 4. Then now, this is a quadratic that we have to solve. So move all the terms over to the same side. So we would subtract 3x minus 4, subtract 3x minus 4. And then this would be x squared minus 3x minus 4 is equal to 0. This one you can factor through inspection. I need two numbers that add to give you -3 and multiply to give you -4. So that would be -4 and +1. So you'd have x minus 4, and then x plus 1 is equal to 0. So we have two possible solutions. We have a 4, and we have a -1. Now, again, just in the interest of saving time, I'm not going to verify this, but for this specific one, it's the -1 that doesn't verify. Okay. Now that's actually very easy to see because if you take x equals -1, you plug it back into the original equation, you have log with a base of x. Well, that would be log at the base of -1. But in addition to checking to see that the argument is not negative, the base can also not be negative as well. So we'll cross this off, and then I'll just put x is equal to +4. And again, if you want to see my full solution for what the verification work looks like, just check out my completed notes on D2L. Again, bearing in mind that on the assigned work and on an assessment, I do expect you to show the verification work. Okay, let's go to the very last page and do one final example. Okay, so it says for part A, we have the equation log of x squared minus 3 log of x is equal to 10. Okay, and it says I want to solve this using the laws of logarithms. Okay, now, left-hand side, we have two logs. They have the same bases. They're 10s. I mean, we don't see them, but they're implied to be 10s because that's a common base. I can't combine them unless I get rid of this coefficient. So we'll just take this coefficient and move it up to the top of the argument. So this would be a log of x squared minus log of x cubed. And then this would be equal to 10. Okay, combine these two logs together using the quotient rule. So it would be log of, since you're subtracting the logarithms, we're going to use division. So x squared over x cubed, and that's going to be equal to 10. Well, we're going to have some things cross off here. So the x squared on the top would cancel off everything but just x to the power of 1 on the bottom. So now I would just have log, and then we're going to have 1 over x would be equal to 10. Okay, to solve this, so even though we don't see the base, it does have a base that is 10. Okay, so convert to exponential form, and it'd be 10 to the power of 10 would be equal to 1 over x. Okay, 10 to the power of 10 is way too big of a number to actually like get your calculator to evaluate. So all I'm going to do here is I'm just going to take these two and just make them switch spots. So if you do that, you would then get x would be equal to 1 over 10 to the power of 10. And we're just going to leave the answer as that. Because otherwise, 10 to the power of 10 is going to be like a ridiculously large solution. Like we do not want to write that down. Now, I will show the verification work for this one. So we'll say verify. X is equal to 1 over 10 to the power of 10. So in the place of x squared here, we're going to plug in 1 over 10 to the power of 10. Same right there. And we'll see if we can get both the left and the right-hand sides equal. So this would be log of, okay, so we're going to have 1 over 10 to the power of 10, and that's going to be all squared. And then minus 3 times log of 1 over 10 to the power of 10. And we're just checking to see if that's equal to 10. And I would just plug this exact expression into your calculator, how I see it right there. And then it will show you that both the left-hand side and the right-hand side are the same. So we have 10 is equal to 10. Okay, now B. We're going to write down an equation that's going to seem identical to the one in part A, but it is not identical. So what this equation looks like is you have log of x all squared minus 3 log of x is equal to 10. Now, what it says here is explain why you cannot solve this equation using the laws of logarithms. Now, specifically what we're doing right here is everything in the equation is the same except for this portion and this portion right here. So the issue we're having is that log of x squared is not equal to log of x all squared. Log of x squared, where you just square the argument, would be 2 times log of x. Log of x all squared. So here, we're not only, you're not just squaring just the argument, you're squaring all of log of x. So this is actually a repeated multiplication of log of x. So this would be log x times log x. Okay, those two things are not the same. Now, the way we're going to solve this is actually a quadratic. Okay, so what I'm going to do is we're going to do a substitution. So here, where I have log of x, and here, where I have log of x, I'm just going to pick a different variable to represent this. We'll say let a be equal to log of x. So now, if I take this equation and rewrite it out with that substitution, it would be a squared minus 3 times a is equal to 10. That's a quadratic. Now, to solve a quadratic, I want all the terms on the same side. So I'm going to take that 10 and move it over to the left-hand side. So minus 10, minus 10. And then I would have a squared minus 3a minus 10 is equal to 0. That's a quadratic that nicely factors. So two numbers that add to give you negative 3 and multiply to give you negative 10, that would be negative 5 and positive 2. So we would then have a minus 5. And then we would have a plus 2 is equal to 0. So then we have a would be equal to positive 5 and negative 2. Now, we're not solving for a here, we're solving for x. So what I now have to do is you have to plug this equation back in. So instead of a, it's actually log of x. So we'd have log of x would be equal to 5 and negative 2. Sorry, this looks like it's a base. Let's make it so it looks like it's an actual argument. Okay, so that's up at the top now. Now again, the base is 10 here. So my two solutions, it would be one solution would be, so let's write it out. So one solution would be 10 to the power of 5 equals x. And your second solution would be 10 to the power of negative 2 is equal to x. Now that negative is okay because that's not an argument or that's not a base, okay? So that's not really an issue. And then what you need to do again is once you get these two solutions, plug them back into the original equation, just see if both the left and the right-hand side verify. But I'm not going to show you that work, okay? Just because I want to save, again, just save time here. But if you do it, they both actually verify. So both verify, therefore x would just be equal to 10 to the negative 2. Or you could write it as 1 over 10 squared if you wanted to, and 10 to the power of 5. Okay, and we have one final part here. It's a question where it just wants us to identify what exactly is the error, I believe. So what it says is a student is solving the equation log x all squared minus log of x cubed is equal to 0. And they try to do a substitution right here, which is they say, they're like, okay, let capital A be equal to log of x. So the log of x, that's all in brackets squared. So that's no problem. You can write that down as a squared. But the issue right here is that this is not log of x all to the power of 3. It's just the arguments to the power of 3. So when they write down a squared minus a cubed is equal to 0, okay, that's wrong. And the reason it's wrong is because it's not written as it would have to be log of x all to the power of 3. And then if it was to the power of 3, then we could write it down as a to the power of 3. Okay, well, since that's incorrect, what would you do to solve it? Okay, let's leave the first term the same. So log of x all squared. Now this one, what I'll do is because that exponent is just attached to the argument but not to the entire logarithm, I can use the power rule to bring it down. So now I'd have minus 3 times log of x is equal to 0. Now I can use this substitution, okay? So now I can replace log of x with a and log of x with a, and then it would look like a squared minus 3a would be equal to 0. Now to solve this one, we would just need to pull out a common factor, which is a, and that would leave me with a minus 3 is equal to 0. And then using the 0 product rule, one solution would be a is equal to 0. One solution would be a is equal to 3. But again, we're not solving for a here. We're trying to figure out what x is. So I have to replace log of x with a. And then I would have here, you'd have log x, okay, because it's not a, it's log of x, is 0, 3, and that'll lead to two solutions. So one solution, again, your base, even though we don't see it as a 10. So one solution would be 10 to the power of 0 is x. And another solution would be 10 to the power of 3 is x. And then again, you can plug both of these back into the original equation and they will both verify. So your answers right here would be, well, 10 to the power of 0, you can simplify that one. You can just write that as being, just as that being 0. And then 10 to the power of 3 would just be 1,000. So if you want, yeah, you can just take these, plug them back in and see if it does make the left and the right-hand side the same. Okay, that's it for this lesson. I know it was quite a long one. Again, like I said, I was dealing with more complicated equations. So the assignment questions you need to work on are numbers 1 through 9. Okay, B and D. For any question that's multi-part. And do 11 and 12. And verify them. Okay, I do say verify because, like I said, when I do check this work, and also if I ask you to solve a logarithmic question on a particular exam, I will for sure ask you to verify the solution. That would be part of demonstrating an exemplary understanding of the material. Okay, that's it. And I'll talk to you in the next lesson.